last couple of days, we've been looking at how does a substance heat up. We predicted that if you constantly added heat to something, you would see a linear increase in the temperature. However, we found something when we started to actually track what happened when paraffin wax was heated and cooled. Instead, what we'll see is at some point there is a plateau before the temperature of that rises again. If the temperature is increasing, then you are constantly adding heat. What happens though is that the heat can either be used to change the kinetic energy of particles, or perhaps the energy is being used to change the potential energy of the particles. So when we talk about kinetic energy, we're talking about how particles move. The more heat you add to those particles, the faster they move until they get into things change. Solids have what we call vibrational motion. Liquids have vibrational and rotational, and gases have vibrational, rotation, and they travel in straight lines into the soft or something, and that's called translational motion. So whenever something goes through a phase change, it has to lose one of those types of motion or gain one of those types of motion. And that is what the input heat energy is being used for. Earlier in the meeting, we calculated how much heat was gained or lost by something when it changed temperature. Today, what we're going to do is look at how much heat energy is gained or lost when a substance goes through a phase change. Do you remember what your formula for calculating heat is?
Oh, Q equals mc delta T.
Okay. What could be the problem with trying to use Q equals mc delta T for this time period? There's no change in temperature. The temperature stays the same. We cannot use this formula in order to calculate the gain or loss of heat. What we need to use is a new formula. I'm going to show you what the new formula is, and then we're going to do some practice with that. Tomorrow, we're going to combine the Q equals mc delta T with the new formula to figure out how much energy is being lost when something like this Q is. So let's see what a few curve looks like this. Okay. This is a little bit different than the one that you did with the paraffin box. So do you want to do this side?
Maybe.
Just let me know. Okay. I'll pause this now. Last week we looked at a heating and cooling curve of a substance that had one plateau. This has two plateaus. Why do you think it has two plateaus? Any guesses? Why do you think it has two plateaus?
Could it be a change in form, like ice to water and water to like...
Okay, so if it was something like water, what would the first plateau probably indicate? Melting, and then the second plateau would indicate? Evaporation. Okay. So anytime where we have a diagonal line, that is when a substance is changing temperature. Wherever you have a plateau, that is a state change. Because the temperature is increasing, the state change rate here is melting. Here, the state change is evaporation. If this was a cooling curve, we had something like this, what would this first plateau indicate?
Water. Solidifying.
Condensing. The second plateau would indicate
Freezing.
going from a liquid to solid, which is freezing.
Freezing.
Okay. If you have a diagonal line before the melting area of the curve, what state is the substance in during this time period? Has it melted yet? What state is it in? Solid. Between melting and evaporation. And then after evaporation, gas. Here, the gas comes before condensation. After you have condensation, you have the liquid. After the freezing, you have the solid. This substance is not water. How do I know that?
Because it's melting at 50 degrees. Is it 30 degrees plus? It's a solid?
Yeah, this is going to change that much. And having a melting point of 55 degrees Celsius. The temperature just put this water melt at
0
degrees Celsius. So there's no way that this is water. This is just a fictitious example to make sure that we're looking at another substance besides water.
Ice cream.
This is your new formula. We cannot use the Q equals MC delta T formula to determine the amount of heat energy lost or gained during a state change because there's no change in temperature. Instead, we use what's called Q equals M delta H. The delta H value that you use depends on what the substance is doing. So fusion is an older term for melting. What did you learn about the melting point and the freezing point in the paraffin wax lab?
What?
Melting point and freezing point.
Melting is around 30 degrees and freezing is around.
The water melts at 0 degrees Celsius. It also freezes at 0 degrees Celsius. So the melting point and the freezing point of the substance are the same. Okay. So heat of fusion is an older word that means melting. But you have to remember that melting and freezing are going to be equivalent values. So if you have a positive heat of fusion value, that means that your substance is melting. But if you have a negative heat of fusion, that means that the substance is freezing. Heat vaporization is for the liquid to gas or gas to liquid phase change. If you have a positive heat of vaporization number, it means that it is evaporating. If it is a negative heat of vaporization, the substance is condensing and losing its heat energy. H is a new letter for us. Oftentimes you'll see references to the fact that this is heat, which is a little bit misleading. Because if it was heat, then why do we have a different letter? It's Q is heat energy. When we talk about H, it's actually enthalpy, and we're considering both the kinetic and the potential energy when we talk about enthalpy, not just heat energy. The units of H totally depend on what kind of a question you're dealing with. If you're dealing with chemistry, generally we use smaller amounts of substances in chemistry So you're going to see the units joules per gram. However, in physics, we're usually talking about devices, and they're going to have much larger entities, and you have joules per kilogram. So you need to be very aware of what units you're using, because whatever the bottom or denominator unit is on the heat of fusion or heat of vaporization value, you need to match your mass units. If you don't, things will not cancel out appropriately, and you'll be off by a factor of 1,000. The front side of this worksheet will be going through today. The back side is for tomorrow, when we start putting these two formulas together. It is really important that you need to question and identify what is the phase change that is occurring, because you get very, very different heat of vaporization or heat of fusion values that you need to use. You should have a data table that I gave you for specific heat. You'll need that to take these questions.
I don't have the reference graph. Well, I feel like they're gonna be better. I feel like they're gonna be better. Like, if she takes last week, I feel like she'd be better. Yeah, they're not gonna be good. Not gonna be bad. That's gonna be like 80s, but 90s.
Oh, this is the table that you should have out in order to do these questions. Let's take a look at page 9 of that data table. This first question says, how much energy is released to the environment by 50.0 grams of condensing water? You need to find water. Are you using heat of fusion or are you using heat vaporization?
Oh, Stephanie.
Condensing water. That's vaporization.
Okay, but remember, condensing is just the negative value of the heat of vaporization.
So it's condensing then because it's going from the
If you take a look at your data table, your heat of fusion value is 6.01 kilojoules per mole, and your heat of vaporization is equal to 40.65 kilojoules per mole.
What does mole mean?
This, actually, what does mole mean?
That is a very good question. Have you ever heard of the mole before?
I've heard of like an animal.
It lives in
Okay, yeah. Okay, the thing on your skin, that is an neuron. A mole is actually a measurement in chemistry. And because we haven't done the chemistry yet, we need to use some other data tables because we don't know how to work with the mole yet. Okay. Just so that you know, when you see the word MOL, that equals mole, and it's a number of something. So for example, if I asked you how many, okay, music festivals going on right now, and we have some piano trios playing. How many people are playing? Great. If you were trying to find a pair of socks to wear, how many socks are you looking for?
3.
No. Pair of socks. 2.
Not if you're a boy.
If you were asked to pick up a dozen buns from Shop Easy, how many buns are going to be in the package? 12. So those are all words that indicate quantity or the number of something. In chemistry, when we say the word mole, we mean 6.022 times 10 exponent 23 of something. So that means that if you were to go to Tim Hortons and ask for a mole of Timbits, they would need to count out 1, 2. That many Timbits for you. That's a lot.
Science. Third one.
So if we look back at the question, it says how much heat energy is released to the environment by 50.0 grams of condensing water vapor.
It's negative V, that's what we're going to use.
It's the negative of the heat of vaporization. It's really important that you identify from the question what it is that you need to work with. The value of 334 is quite different than the value of 2,260. In this question, you're being asked for the amount of heat energy, which is Q. You're told that you have 50.0 grams of water. Your heat of vaporization is 2,260 joules per gram. This needs to have a negative in front of it because it's condensing. The other clue that alerts you to the fact that you need to have a negative value is it says how much energy is released to the environment. That means that the water is losing heat energy to the air. The formula is Q equals M delta H. And in this case, it's your heat vaporization. Your mass is 50 grams. Your heat vaporization number is 2,260 joules per gram. Gram divided by gram is 1. So you're going to be left with joules. Please calculate the heat energy lost by the water.
Yeah, but 6, 8.
You get a very large number. There's a couple of things that you can do with that number. I would suggest that since it's a very large number, you express that number in scientific notation. You get 3 sig figs to work with, because you have 3 sig figs in both of the numbers that you started with. The other thing that you could do is you could change your answer into kilojoules. In 1 kilojoule, there is 1,000 joules, which means that you would have negative 1.13 times 10 exponent 2 joules.
She wants expressing this
What does that work? What is on the bottom?
Can you go back a slide? Miss Patterson?
I'm going back.
Oh. I didn't think you could hear me. How come it's in joules in the very last answer?
Sorry?
How come it's in joules in the very last there?
Because this is in joules.
No, on the bottom it's supposed to be kilojoules.
Oh, pardon.
Oh, you're good.
I forgot
It
to
doesn't
say.
know how to read.
Joules divided by joules is 1. Thank you. Okay, let's look at question number 2. Question number 2 says, calculate the amount of heat needed to melt 35.0 grams of ice at 0 degrees Celsius. Are you working with the heat of fusion value, or are you working with the heat of vaporization value?
Fusion.
Fusion, because there's the word melting and the stem of the question. That means you have to use either this data or this data here, depending on what mass your ice is given to you in.
We're using 334 grams.
The 334 joules per gram, because you have 35 grams of ice. So this is an example of a chemistry question. This is a smaller amount of ice. Okay. Give it a try. Please note that it's asking you to express your answer in kilojoules. One of the questions that was just asked is, what exactly are you trying to calculate the heat to? Okay, I want you to imagine that this is the mass of ice that you are trying to melt. Why is this ice cube melting in my hand?
Because your hand is hotter than 0 degrees.
So the heat is transferring into the ice cube and is causing those solid water particles to go to a liquid state. So what we're trying to do is put a number to this process. How much heat, yes, is going from my hand to the ice cube. When I set up my question, I like to pull out the keyword that is identified in the statement, so that I have a reminder that I am dealing with heat of fusion, and because it's melting, I have to put heat energy into that ice cube in order to melt. So I know that my heat of fusion value has to be positive. If you were trying to put that ice cube, or the ice cube tray full of liquid water into the freezer, you would have to put a negative heat of fusion value because you're trying to take away the heat from the ice cubes to make it go into the solid phase. So my mass is 35.0 grams. My heat of fusion value is 334 joules per gram. I'm calculating how much heat is actually lost in this process.
It's not
So-
so it's not
So that can be 1.17.
So we have 35 grams
instead of milk.
divided by 334 joules per gram.
Well, I could put milk in.
This gives you an answer of 1.2 times the 10 exponent 4 joules.
What? That is not what I got.
What?
We got 11,690.
Okay.
And then leave 360.
Three.
With 1.7.
Yeah.
Kill Mary. Well, the rest are.
You get 3 sick pigs.
It was here.
So 1.17. It asks you for your answer in kilojoules, which means you need to do the conversion ratio. 1.17 times 10 exponent 4 joules. It are 1,000 joules in a kilojoule, which should give you 1.17 times 10 exponent 1 kilojoules. All right, lots of yeses there. That's great to see on a Monday morning. Mondays are always harder to wake up
Mondays
those
are better
brain
than
cells.
Fridays.
That's awesome. You are going to work on the remaining questions, all the way up to question number 8. Please make sure that you do this, because tomorrow things are going to get a lot more complicated. If you look at the next page, there's a practice problem of just how complicated that's going to be.
But I don't want to.
Make sure that you practice this stuff so you're solid with your engaged calculations, and you'll be set up for success tomorrow.
Close it.